Hi, everyone, and welcome to Becker Breaks It Down. In this episode, we are going to convert exponential models. And you're probably wondering what that means. Okay, so we work with two types of exponential models. I call them non-continuous and continuous. Okay, the non-continuous, that's your discrete growth, where change is happening at specific intervals. Um, in many of the problems that we do, it's happening like every year. Okay. Whereas continuous growth would be happening at any given moment. Okay. And so here we have the difference side by side, but here we have the difference together. Okay. So it is possible to model that discrete growth. Okay, so that non-continuous exponential function, it is possible to write an equivalent continuous exponential model. Okay, and so looking at this diagram here, this model is suggesting that y equals 2 to the x power and y equals e to the 0.693 x power are equivalent. Okay, therefore, 2 is equal to e to the 0.693 power. So, in other words, for all base b exponential models, we can say b is equivalent to e to the k power. And that's how we can convert from a base e exponential function to a base b exponential function. But how do we go the other way around? How would I go from base b to base e? Okay, and so basically, think about it. Like we were solving um, exponential equations earlier in this chapter. I'm just going to go back to this page. Okay, and so what we have right here is an exponential equation, and we solved that exponential equation by taking the natural log of both sides. So what if I did that? What if I took the natural log of both sides? Okay, that is really messy, so I'll write it here. So I take the natural log of b, and I take the natural log of e to the k power. Well, as you know, the natural log of e is equal to 1, which means that the natural log of e to the k power is simply equal to k. So this would be our conversion factor for finding the value of k given a base b function. Okay. And so now let's go to this nice little table that organizes it all. Okay. So talking a non-continuous base b exponential function, I can figure out what is b, right, by calculating e to the k. Likewise, I can calculate k by calculating the natural log of b. I think this little flow diagram shows it a lot better, right? So if I am given a continuous base e exponential function, I can convert this to a non-continuous function by calculating e to the k power, because that is the value of b. To go the other way around, if I'm going to start with a non-continuous base b function and I have to go to a continuous one, I need to calculate the natural log of b, and that will tell me what k is. Right? So the title of this particular lesson was Converting Exponential Models, and this is how we're going to do it. So example 1 says fill in the table below, assuming that t is measured in years, round k and b values to 4 decimal places. Well, in that first row, I'm given q equals 6 times e to the negative 0.04 t power. So there are a few things that I know about this. First of all, this is our continuous function. So when it comes to the continuous rate is my k value times 100%. So I'm looking at 4%. That negative here simply means it's a decay function. Okay. The other two things in this row, I'm going to have to convert. And so according to my little flow diagram, this is where I'm at. I have a continuous function and I want the base b equivalent. So I need to calculate e to the k power. So I need to, in my calculator, type in e to the negative 0.04 power. And this is going to give me the value of b, right? So I already did that to save us some time. Okay, I calculated, let me highlight this for you, e to the negative 0.04 power, and this is what I got. So that's the value of b. In order to find that rate, you might be wondering where this rate of 3.92% came from. This comes from taking that b value minus 1 and multiplying it by 100. So base minus 1 times 100, we've done that calculation a couple of times before. So it's pretty easy to convert from one model to the other. We simply need to calculate. So in the second row, I have q equals 1.2 to the t power. So I'm given a non-continuous exponential function. In order to get the equivalent continuous function, I need to calculate the natural log of b. This will be equal to k, my exponent. So in my calculator, I'm going to calculate the natural log of 1.2. So naturally, I've already done that. And I said the natural log of 1.2 was 0.1823, and that's the value of k. All I had to do was calculate the natural log of 1.2, and that's how I got my exponent. Looking at the other three columns, this is a growth function. I knew that because my base was greater than 1. That rate, once again, came from going base minus 1 times 100. And the continuous rate, once I knew what k was, I simply went k times 100, and that's how I got my continuous rate. So why don't you pause the video now, try out that last one for yourself, and then check back in with me. So let's see how you did. So you should have calculated the natural log of 0.91. The natural log of 0.91 is how you're getting this k value here of negative 0.0943. This is a decay function because our base is less than 1. The rate, and we're talking the non-continuous rate, is 9% because you go base minus 1 times 100. And then your continuous rate is your k value times 100. And so that's how you convert from the non-continuous discrete exponential function to the continuous base e exponential function. It's all about a simple calculation. To go from continuous to the non-continuous, simply calculate e to the k power. To go from non-continuous to continuous, simply calculate the natural log of b. And that is how Bakker breaks it down.